hope that you realize that I put answers to those up on Canvas. I hope that you realize, or that you took some time over that time that you had on Friday to work on homework. Okay, I did pare down the assignment from what it had been, because that was just like all the good problems, to the ones that I thought were most relevant and most important. I'm going to take some questions in just a minute, but there is one more piece of content that I want to make sure that you've seen, so I'm going to do that first. I do want to reiterate right now to you that there is a lot of content in this unit that you and I did not talk face-to-face about, okay? A lot of that had to do with the nature of the schedule, okay? And also the fact that I feel like it's making you feel that after doing labs, you could really, assimilate into your concept of how circuits work just by hearing it and seeing the video. But if there are things, as we're going through today, that you have questions about, today is your day to ask questions, okay? Like I said, I have one thing to do, and then the rest of the day is yours to drive. So we can do that all as a group, or we can do that piece by piece. That's up to you. Does that make sense? Okay. What I would like for you to do right now is to pull out notes for just a minute. I just got a little bit of stuff that I want to go through with you, and then it will be yours. Then the day will be yours to plan from. The reason I will be completely frank about this, that I didn't cover this initially when I was kind of planning through the unit, was not because I didn't think it was important. In fact, I do. But I went back through and I read the AP standards again when I was kind of trying to plan our time together. And it's not in the list. But then when I went back and looked at some of the AP problems, it is in the problems. So there's a little inconsistency there. So I want to make sure that you have it. Does that make sense? Are you with me? Okay, so I want to make sure that you're aware of this. The concept is not difficult. But if you've never heard of it or seen it in this context, it does not make a lot of, or it might not make a lot of sense to you. So the concept is energy and power dissipation, okay? So we know that when electrons move around a circuit, they have a bunch of potential energy that they start with at one terminal of the battery. And they have to lose that potential energy by the time that they get to the other side of the battery, right? That energy has to go somewhere, because energy does not just poof go away. Where does that energy go? Into other types of energy. Where does it dissipate usually? In the resistor primarily. If the resistor doesn't exist and you just have a piece of wire, then the wire will get really, really hot. Okay? Because then the wire is the only thing that can dissipate that energy. And that energy has to be dissipated from here to there. It's got to happen, because we're going from high to low. Got to go somewhere. So that energy and power, and remembering, power is just, how do we define power? Do you remember? Yeah. So power is just change in energy. Or sometimes we define it as work, but either way, over time. So we're talking about this in terms of a circuit. So we're changing that electric potential energy into some other kind of energy. So power for us is the change in electric potential energy over time. And that's really saying how much energy is being dissipated in this resistor or in this light bulb or this toaster or whatever it is that you have plugged in. Okay? We haven't really talked about energy. This is something that we haven't really dug into, except that we have talked about this concept of voltage. Do you remember, friends, how we defined voltage? It's been a few days now. What is it? It has to do with charge.
How much electrons?
Yeah, it's the electric potential energy per charge. So the very first day that we talked about voltage was the only day we really talked about energy until today in this little unit, right? So we said that voltage was equal to I'm not going to say change, and I'm just going to say potential energy. But remember, that's just the change, right, from one place to another. Okay, divided by charge. Well, I want to put potential energy in here, so that's just going to be voltage times charge. Is that okay? Just looking at our definition, multiply voltage, energy per charge, times charge, gives you just energy. So I'm going to write this as voltage times charge divided by time. So another way to write power is just voltage times Q over T. Okay, that's great, Miss K. Thanks a lot. But now I want you to look a little thoughtfully and be a little bit clever here. So you got this thing that I've put in yellow. What is that? Q over T. What's that?
Current.
Oh my gosh! So now this is where it gets cool, friends, because now the power dissipated in a circuit or in a part of a circuit is really just equal to the voltage across that part times the current through that part. So if you know the voltage and you know the current, then you're set. Okay? So this would be a big thing to put a box around. I didn't actually look, but I'm pretty sure that exists on your equation sheet. Let's take a look. Boom! There it is. There it is. P is equal to I delta V is how they wrote it in there. Okay? Just a friendly little hint. So this is the one that you can always use, and it's always going to get you where you need to go. But sometimes you might see a couple of different expressions. So I just want to show them to you just so that you're aware. For ohmic devices, and so I hear giggling, ohmic, because it sounds goofy, right? But do you remember what an ohmic device is?
A device that obeys Ohm's law.
It's really simple, right? A device that obeys Ohm's law. Okay? So something that follows V is equal to IR, or my preferred way to write that is that the current is dependent on the voltage across some resistor. If a device obeys this, then we can write power in different ways. Now, these are not magical equations. This is just rearranging things to make your life easier. That's all I'm doing. So if I take this equation here, the P is equal to IV, and instead of V, I write IR, I can say that P is equal to IR times I, or let's make that a little bit less ridiculous, and say I squared R. So as long as you're talking about an ohmic device, again, one that follows Ohm's law. For example, not what? What is the big one that's not ohmic? Light bulbs. Not ohmic. Don't do it. Don't make the mistake I made, right? Okay? So P is equal to I squared R. You can use that. Then you don't have to find voltage, as long as you know the current and the resistance. Okay? Just a little hint. One other thing, because we could do it one more time. Same story. We've got this equation. There it is. So P is equal to, instead of the I, I'm going to write V over R. So I've got V times V over R, or a fancier way to write that is V squared over R. These three statements are exactly the same for an ohmic device. I used to have students who would like, oh my gosh, I can't remember which. Like, as long as you know this one and it's on your yellow sheet, you're set. I just want you to be aware that you can play with those and you can figure them out kind of piece by piece. How we doing? We okay? Yeah? Cool. All right. So I have one little electric power problem that we could work on if you want. Otherwise, I can just leave you to say, oh, I know how to plug things in. Let's move on. Opinions? Do one just for kicks?
Let's hit it.
Why not? All right, here it is. A circuit provides a maximum current of 20 amps at an operating voltage of 120 volts. Oh, yeah, watts? What's that? What's that a measure of? Power, right? So how many 75-watt bulbs can operate with this voltage source? Okay? The hint here is not to think about it too hard. Use dimensional analysis to make your life better. And then once you've done that, at 12 cents per kilowatt hour, what's that about? What is kilowatt hour measuring? Just real quick for you. Kilowatts. So what's a kilowatt measuring? Power times time. So power times time is really a measure of what? Energy. So kilowatt hour is just another unit for energy. Okay? So how much energy? So you're paying per unit of energy, right? 12 cents per energy. How much does it cost to operate these for 8 hours? Okay, I'm gonna let you work on this for just a minute. It's really dimensional analysis, my friends. You can do it. Give it a shot. All right, physicists. So how are we doing? Did we get part A? Did we get part B? Where are we at?
We got part A.
Okay, let's do part A. So let's do part A. How are you going to do part A? Use the formula, right? The formula says that power is equal to what times what? Voltage times current. The voltage is 120 volts. The current is 20 amps. Oh, I'm on freeze. You can't see all this great stuff that I'm writing. There you go. Now it's great. 120 times 20 is 2,400. 2,400 what? Watts. For sure. Right?
Divide by 75.
If you've got 75, are you okay here or no?
No.
Okay. Why not?
I know you have to do 120 times 20.
Okay.
I got 2,400.
Great.
But so a volt per amp is a what?
A volt times an amp. A volt amp is a watt.
We call them volt amps.
Is a
I mean, yeah.
We call them volt amps.
No.
Stop just watts.
okay, so
Amplify.
So, are you okay with that, or do you want me to explain
now,
why?
I guess now.
I found this a different way.
Yes. Okay. Thumbs up.
I used
All right. So then, guys, I just want to make sure we have time to go through everything that you want to go through today. I mean, I guess it's your call, but that's okay. So you've got 2,400 watts is the amount of power that you're dissipating, right? You got 75 watt bulbs. So if you've got 75 watt bulbs, you've got 2,400 watts of power divided by 75 watt bulbs. Watts per bulb equals how much?
32.
32 bulbs. Okay. Yeah. What happens if you put 33 bulbs? Was this like the international sign for it will explode? It will not explode.
The lights be dim.
The lights would be dimmer. Yeah. 75 watts is like the maximum that it would, that's the, right? Because if you go to Menards and you're shopping for light bulbs, the wattage is how bright it's going to be, right? So you buy a 30 watt bulb, it's going to be dimmer than if you buy a 60 watt versus 100, right? But that's running at maximum, right? At its maximum. But it'll still light, it'll just be less bright, and then it won't be dissipating 75 watts at a time. What's up?
What are these lights at?
I don't know.
Are you tripping?
Right.
And I don't mean that, like, I
No, I mean
genuinely do not know. Yeah.
We can calculate it.
Not right.
Yeah, not right now. All right. So then part B. 12 cents per kilowatt hour. How much does it cost to operate these bulbs for 8 hours? So how are you going to deal with this? Multiply and stuff, right? So let's just go through it, just one little step at a time. So I'm going to say 12 cents per kilowatt hour. And literally, without thinking about physics, I'm just going to write this down. So it's money per kilowatt hour.
Okay.
How many watts are we talking about?
Kilowatts.
2,400 watts or 2.4 kilowatts? I've got kilowatts on the bottom here. I want to know money, don't I? So this is like, you could do this, again, no physics in your brain, just trying to cancel out units. Okay? This is one of those tips. Sometimes they're going to give you something you've never seen before. You don't get scared and run away. You say, okay, let's look at units and see if we can figure something out. So I want to know money because it says how much does it cost. So I want the money to stay there, which means I need to get rid of the kilowatts. I know something in kilowatts. It's the 2,400 watts, which is 2.4 kilowatts. So here we go. We're going to multiply by 2.4 kilowatts. How we doing? We okay? Kilowatts, bye-bye. And then it says how much does it cost to operate these bulbs for?
8
8
hours.
hours. And I've got hours down here. I got to get rid of it. If I've got hours on the bottom, where am I going to put hours to get rid of these hours?
Up top.
Holy cow! Middle is not an option. See you later, see you later. And now if you look at your units, the only units you have left are the money units, right? And that's the unit I want. So life is good. No physics required here. Right? I mean, I guess you had to move this over. That's just, that's not physics either. What do we get? How much?
$23.04.
I got $2.
I think $2.
It's $23.
$2.30.
and then
Whoa, you're like
0.4 cents.
defensive of any, I don't know.
So the power company's going to round that up though. So let's go.
They would, yeah.
All right.
Anything over.
How we doing, team?
They do it.
Got it? Okay. That was the piece that I wanted to make sure that you saw because I want to make sure that you're aware of that. I don't know, prior to tomorrow and or prior to the 7th. Okay? The other things on my list to do today were to answer homework questions, to do any review that you wanted for the test. I will tell you that I've looked through the test. I haven't solidified it, but the test that I'm working on will have some multiple choice. I don't know, 2 or 3, maybe a ranking task or 2. Okay? Similar perhaps to the ranking test that you saw on Friday. Is there anybody else that was not here Friday that needs a copy? Okay? And then there might be one kind of open responsey kind of question. Okay? I haven't solidified it, so I'm not saying it will have all of those things, but those are kind of the things that are out there in my awareness. But I will write it for a 1-day test. Because starting Wednesday, we will start this. Okay? I do want to tell you that I will introduce all of that review stuff on Wednesday. I know some of you will be in and out. I totally get that. That's how the world is. But know that if you're not here any day, yes, you will have work to do. Yes, you will have things you need to turn into me electronically or physically. Okay? Okay. Any questions you have on homework that you want to go through? Is there anything that I can help you with? Either homework or this or anything. Henry, you got some stuff?
Yeah.
What's up?
Question 9 and 10.
Can you remind me of the chapter that we're talking about?
23.
I thought that's what it was, but I just haven't looked at it for, a couple days, so. 23. Questions 9 and 10?
Yeah.
That sounded really certain. Are you feeling really certain about that?
I was trying to remember them. It's like I circled them.
Gotcha.
I don't know. I don't know if I actually.
Problem 16. Make up.
And problem, what was that, 16? Do you want me to go through those?
Yes, please.
Okay, here we go. So question 9. Shh. I know that sometimes people are like, oh, I've done these. If you've done them, then find something else to do. Study some physics, but don't make it loud because I need to be able to hear myself think and be able to converse with those around me. Okay, so it says figure 23.9 shows 2 circuits. So I'm just going to draw them real quick. I'm just going to draw one battery quick, choop, choop, like this. And then the other one has got 3 resistors. And the 2 batteries are identical. All 4 resistors have exactly the same resistance. It says, is the potential difference, that's delta V, larger than, smaller than, or equal to CD? So the potential from A to B as compared to C to D. What'd you say? Which one has a bigger potential difference? Isn't that what the question is saying? Larger than, smaller than, or equal to? Equal. Same battery, right? Same battery, that means same potential difference. That means that any electron leaving here and any electron leaving here are going to have the same amount of energy per charge as one another. They have to lose that as they go around the circuit.
So they're on the same potential difference.
They have the same potential difference. They have the same amount of energy per charge. So they're lifted up the same height, if you think about it as front. It's true. Just means it has to go through more things. Doesn't mean that the current will be the same, but it means the potential difference across there is the same.
What's the potential difference? I don't know.
Energy per charge. Potential difference is voltage. Voltage, potential difference, electric potential difference, electric potential, potential, any other combination of those words, or EMF. All of those things mean the same darn thing.
They mean like voltage.
They all mean voltage. Yes.
Alright.
That get you ready to go?
Yeah.
Cool. All right, that's part A. Part B says rank in order from largest to smallest the currents. So let's label them here. So this is I1. This is I2. And this is I3. Okay? It says rank in order from largest to smallest those three currents. Yeah.
I1 has the greatest current because there's only one resistor,
Okay?
right?
Sure.
And then I looked at mine and said I2 and I3 equal to each other.
Okay?
I don't understand because in between I2 and I3 there's a resistor.
Indeed.
So shouldn't like the current be lower going to the resistor?
No. So and a lot of people want it to be, right? Which is why I like this question. Okay? If you only have one path for electrons to follow, then they're all going to travel at the same rate. Charge per time is going to be the same for all of the electrons going through this circuit. So they're all going to travel in this direction. The electrons go this way, current goes this way. I'll say something about that in a minute. But anyway, all of the electrons go through here and through here and through here. I2 and I3 have to be the same.
Is that because current in has to equal current out?
Exactly. Yep. It's the junction rule. It's like the least exciting version of the junction rule. No junction, no addition. I mean, that's really what it is. They all got to come out, right? And it's conservation of matter. Right?
Conservation of current.
I mean, yeah, but it's fundamentally just conservation of matter, right? Can't destroy it. It's got to be there. It's got to go one place to the other. Yeah.
So if it was a parallel instead of a series,
For sure.
that change?
Yeah, I think that's the next question. That's going to be question 10. So hold on to that for just a second, and then we will absolutely do that. But the key here, and this is from Kirchhoff's rules, you guys did this, right? You measured the current going, I think it was just 2 of them. But the current through this resistor and through this resistor and through this resistor have to be the same. Because where else are they going to go? What's that? In series, correct. Yeah.
So in series, if all the resistors are the same, the current does not change.
Even if they're not.
Even if the resistors aren't the same, the current still doesn't change.
Right. So let me make sure everybody hears this, you guys, because this is at the fundamentals of this stuff. I need to make sure you get this. Okay? Ohm's law says that the current is dependent on a voltage being applied across resistors. Okay? The current in a series circuit is determined by the voltage across the battery and the total or the equivalent resistance. So even if this was a tiny resistor and these two were huge, they would all have the same current all the way through this circuit. Because otherwise you'd have a buildup of electrons somewhere, and then you get a bulge in the wire. Right? That's not how it works. You with me there? Is that okay?
Yeah.
Kind of ish. Okay. So, let me put it this way to you. I'm going to give you a little bit of an analogy because hopefully this will help. So, there's an analogy that I kind of like that involves going grocery shopping. Okay, so if you go to pick your favorite grocery store and you're going to check out at the lane, right? And there's only one lane open, then everybody has to go through that lane. And the rate of flow is just going to be the same for everybody. You with me there? Okay? Let's say that you happen to get one of those really, really awesome checkers who goes really fast, like doesn't start talking to you, doesn't ask how the weather is outside, right? Just like, then the current, the number of people through there per time is going to be fast. You with me there? Okay? Let's say you have that super fast checker, but then you happen to have a bagger who's really slow. Are you with me there? Like, ooh, is that soup good? Right? Okay? So even if you have a fast checker, if you have a slow bagger, the current, we're talking 2 resistors there, right? Okay? The current is going to be the same through the whole thing because you're not going to have a buildup of people in between one and it doesn't happen that way. So the current is just going to be the same going through. Okay? So far, so good? But the current is going to be different than if you just had one person, just a checker, that's the express line, right? So like whatever, it's not going to take very long. Now, the next question, the one that Kate was referring to, is if we have a parallel circuit. So that would be like, lane 3 is open and now lane 4 is open as well. So hot diggity, now we've got 2 lanes, 2 options. That means that the current is going to go up. The number of people, the number of grocery shoppers per time to get through is now up higher because they can get twice as many done. Now, this comes to exactly what I think you were asking, Kate. And maybe you've been in the situation where there are 2 lanes available. You got the speedy checker and you got the super slow checker. Okay? This soup looks great. I didn't know we had plums out already. We've all met that checker. And they're very kind and lovely. But if you're in a hurry, like, oh my gosh. But if you have a huge line for the super fast checker, it is still going to be to your advantage at some point, right, to go through the slow checker line because you're still going to get through faster. So if you have 2 lines, so it would be like parallel circuit, there will still be some current through the slow checker, even though it's not going to be as much current as through the fast checker. Okay? Does that kind of make sense? Ish? Isaac, you look unhappy with me.
Can you say that again?
The whole thing?
No.
I recorded it all. You can just listen to it again.
No, like the end, like the slow one.
So if you have a slow checker and a fast checker,
Yeah.
if you're way back in line, you may take the slow checker.
Yeah.
If that person has a shorter
But
line,
they're gonna get the same.
because the current, you're still going to get through faster than if you wait for the fast checker, right?
Mhm.
Yeah, that's what I'm talking about.
Mhm.
Is that okay? Okay. So we answered question 9, I think. I'm going to look at question 10. So question 10 is essentially the same question, but it's for a parallel circuit. So I've got this one versus come on. This one. And I've got that's D and C and A and B. And this is I1, I2, I3, I4, and I5. So this is a parallel circuit, right? And it's a plain old circuit. So part A says, compare, here's E and F. Compare the potential difference across A, B, C, D, and E, F. How do they compare? All the same resistors, all the same batteries. A, B, C, D, E, F. What?
What's it asking if it's all the same?
Potential difference. Voltage. Electric potential difference. Electric potential. Yeah.
The voltage is all the same for like A, B, C, D, and E, F.
Uh-huh.
I thought in a parallel that the current didn't get down to the far one. I only chose once bus. Resistor to go through.
Okay, so let's do voltage first. Hold on just a second. And then we'll get to current. Is that okay?
I like three.
They are. Except that the voltage here, so the voltage here, the voltage here, and the voltage here are all the same. So the thing that's important to know is that if an electron chooses, and I want to be clear, electrons are not sentient beings, and so they're just falling, right? They're like the frog that falls. It's not that they're like, whoo, this resistor looks prettier, I'm going to go with, like, no. Like, that's not how it happens. That's not how it works. I want to be really clear about that. It's going to fall, and if it falls this way, it's got to lose all of that electric potential energy here, just as if it went through this one, just as if it went through this one. The length of the wire does not matter. The wire is essentially a zero resistance. Okay? The length of the wire does not matter. So they could be one way over here and one way over here. Now, those of you that go into electrical engineering, you're going to start fighting with me in about 3 years because then it will kind of matter. But for our purposes, doesn't matter. Okay? Potential differences are all the same. Is that okay? The current, though, is where you were getting a little bit frustrated. Is that true?
What?
Go ahead.
I was watching the video where you explained the sheet.
Yeah.
Was it the Kirchhoff-Ohm's law?
Yeah.
And you said that. So you're saying that electrons go all the way to the last one? And then
Sure
go,
they do.
Or do they? Is that what they do, or do they go to the middle one?
Sure. Some of them.
I thought you said they only. Go
Every
through one
electron only
resistor.
goes through one. But there's more than one electron, right? There are thousands of electrons.
So they're
There
all
are millions of electrons. So one electron is going to follow this way. Another electron's going to go this way. Another electron's going to go this way.
Okay, that makes more sense.
Is that better?
Yeah, because in the video I thought you said they only followed one path, like all the electrons.
If I said it that way, I didn't intend to.
Yeah.
Each electron will only follow one path, though.
Alright.
So maybe that's what I said, and maybe you just interpreted it differently.
No.
They move so slowly that unless you leave that circuit on for, I don't know, a long time, it's gonna, it might get from here to here. Right? Like these electrons are not moving fast.
How's the light laid out?
He wasn't here that day. He wasn't here that day, right?
I missed the video.
I know, you gotta watch the videos. Watch the videos.
I know that one.
All right.
Good, there's already electrons.
Rank the currents for me.
Obviously, I3 is my greatest.
Obviously, I3 is what? Okay, obviously. Why obviously?
Because that's what the answer said.
Obviously, I read the answer and it said that I3 is the biggest. Why? I agree that I3 is the biggest. Why is it the biggest?
Is that I3 above C?
Where is I3? Yes, this is I3 up here.
I don't know.
Why is, guys, this is not trivial, so I want to make sure you understand. Why is I3 the biggest?
It's at the positive side, and it's at the start of the positive side.
Well, so is I.
So is I1.
I3 is in a parallel.
But one's a parallel, one's
It's the whole current.
So let's think about it in terms of grocery shopping. Think about it in terms of grocery shopping. If you've got one fast checker, right, versus three fast checkers, you can have a higher current or a lower current. You have three fast checkers.
Higher
Oh,
current.
right.
Higher current, right? More people going through. So if you got 3 lanes open, the total current is going to be higher overall, right? Coming out here. Question.
Is I3 equal to sum by 4?
I3, say that one more time.
Is I3 equal to sum of the currents of those?
No, because we got to have this one too.
but it's all.
What's that?
In like I4 and I5 and then that.
And I6? Yes. If this was I6, that middle one, then I4 plus I5 plus I6 would be equal to I3. Yes.
What? So is I3 like I total?
Yes, this is like the total current going through this circuit.
So
Also, like all the electrons.
so how do we know that that's the total one then? Like if it's closest to the battery?
So if I had
The positive.
no, because if I had one down here that was like I17, I'm going to call it that just so I don't get confused. I17 and I3 would be exactly the same.
So
Because the current here and the current here has to be the same. In and out. It's just that some of the current's going to go here and some of it's going to go here and some of it's going to go here. So this is the junction rule. This plus this has to equal this, which is the same as this one. Yes or no? You can say no, and that's okay.
Oh,
no. I know it's the junction rule, but I don't understand like how you choose which one is supposed to be the sum of these plus these.
So I'm going to draw a different picture because that one's getting gross.
I3 is the total because it doesn't get split up
all those
into,
areas.
because there are no junctions technically where I3 is, but once it hits those two parallel bits of it, then it has to.
Oops, these are going backwards. Sorry. Oops. There we go. All right. All right, let me show you real quick. So I marked all of my currents in this picture. Yeah? So my current is going to come out here. That's all of the current. That's the total current. That's all of it. Every electron per time, right? So you like take a little cross section, count the electrons. Go, 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 right? That's how you get current, okay? All of the electrons that go through here, some of them are going to go through this resistor, the B. Some of them are going to go through this resistor, the C. All of the electrons are going to go through either B or C. So if you add up the electrons that go through B and the electrons that go through C, that has to be the same as the amount that started. And then, at some point, they're going to come back together, right? And that's going to be like D. So these two are the same.
Okay.
Okay,
So current starts at the positive and voltage starts at the negative.
current starts at the positive, yes. So here's the annoying thing, okay? We can shake our fist at Ben Franklin because he screwed it up. He had a 50-50 shot and he messed it up, okay? He was the one that decided that when you rub the bunny fur on the glass or whatever it was, that the thing you pull off of one onto the other is negative. He decided he called it negative. He screwed up. He should have called it positive. Because we now know that it's the negative thing that moves. Are you with me there? It's the negative thing that moves, so the negatives move from the negative terminal to the positive terminal. But prior to us discovering electrons, because that didn't happen until much later, we just decided that current was always going to go from the positive to the negative. So here's the weird thing. We're going to write this down because I want to make sure you get this. Here we go. Current flows from the positive terminal to the negative, okay? But electrons flow from the negative to the positive. 99% of the time, you're going to see stuff about current. Ben Franklin screwed us up. The actual electrons move the wrong, in big air quotes, way. Because they're negatively charged.
To try to reconcile it, you can just say that they're moving in high current as well.
Right, which is what I do. But current still goes the other way. What's up? Current is charge per time.